Good day everyone. Today we will be discussing how to model mechanical systems using spring elements. Thereby we are going to determine natural frequency for the damped or undamped single degree of freedom systems as part of the course Me22088. My name is C. Sendamarikannan. I am Associate Professor in the Department of Mechanical Engineering at SVC. Welcome. We are diving into the fundamental concepts of spring elements. Springs are ubiquitous in mechanical systems, acting as energy storage devices and providing restoring forces. Understanding their behavior is very crucial for analyzing and designing a wide range of applications. Let's explore the different configurations and how they affect the system's response. System instance, it may be shock observers, for example. Let's start with springs connected in series. Imagine two springs K1, K2 hanging one after the other as shown in this figure. In scenario like this, we see them at rest. When we apply a force of W as shown here, the springs will stretch. The total stretch denoted as delta is the sum of individual stresses of each spring. This free body diagram shows and visualizes the forces acting on the each spring. Notice that the force is the same throughout the series combination. Let me consider the springs in parallel. Here both springs are attached to the same point and experience the same displacement. In this, we see them at rest and we are getting the deflection, so that the total force is the sum of the forces in each spring. That means by writing it here, we can see it that the total force is the sum of the forces acting on the spring 1 as well as spring 2. Also, we have some kind of springs which are connected in series. If we have two springs as shown like this here, it is connected in series. If I apply force W, see here I am applied a force W, the resulted individual stretches will be like delta 1 for spring 1, delta 2 for spring 2, such that the total stretch, that means the deflection, is going to be equal to the summation of deflection of the first spring plus summation of deflection of the second spring. Here the free body diagram for the spring in series clearly shows us how the forces and displacement in each spring element. Finally, let me see this, the free body diagram of the spring in series. You see that if the force is applied, the force is reacting on the springs. In the spring of K2, we are getting that load is stretching the spring K2. At the same time, the work done on the spring is given as stiffness into deflection. The same force is going to be applied on the upper spring K1. There we are getting K1 delta 1. So here the W is same. It is not plus, that is, it is not W equal to W1 plus W2. Here only the deflection is del 1 plus del 2. Understanding this basic spring element configurations is essential for analyzing force displacement relationship for designing any mechanical systems. By applying these principles, we can predict the behavior of complex systems involving springs and optimize their performance. Let me see that in the next slide. We are going to explore how springs behave when they are connected in different ways. It's just continuation of our previous slide where we see that springs are in parallel and springs are in series. Understanding these combinations is very crucial for designing and analyzing systems with multiple springs. Let's begin with springs in parallel. Imagine that Several springs are side by side, all attached to a same object like this. When you apply a force, each spring stretches by the same amount. But how do we find the overall stiffness of this combined system, the equivalent spring constant? So we have to find out equivalent spring constant. It is denoted as K suffix E equivalent. For springs in parallel, it is simply the sum of individual spring constants. If we have n number of springs with constants, that means it is K1 plus K2 plus K3 and so on up to K suffix n. So this is the formula to calculate equivalent spring stiffness when the springs are arranged at parallelly. Now let's look at springs arranged in series. In this arrangement, the springs are connected end to end like this. When you apply a force at these springs are arranged in series, each spring experiences the same force, but they may stretch by different amount depending on their individual stiffness. Finding the equivalent spring constant for springs in series is a bit different. It is the reciprocal of the equivalent spring constant is equal to the sum of the reciprocals of the individual spring constants. So for n springs in series, the formula is 1 by k equivalent equal to 1 by k1 plus 1 by k2. That means it is summation of till the nth stiffness. This means that the overall stiffness of the springs in series is actually less than the stiffness of the weakest individual spring. Hence, see that this understanding will help you to simplify the complex spring systems and calculate their overall behavior. Remember, parallel connections increase stiffness while series connection decrease it. These concepts are very fundamental in various engineering applications, from designing the suspension systems to analyzing vibrations in structures. We are going to solve a problem involving a spring mass system. Our goal is to find the natural frequency of this system as shown in this figure. Let's start by understanding the given information. We are given three spring constants K1, K2, which is equals to 1500 newtons per meter. K3 equals 2000 newtons per meter. We also know the mass is 5 kg. We need to find the natural frequency of the system. This is the very simplest problem. It is the first problem we are doing so in this springs systems. Here, the figure representing the system shows that we have the three springs which are connected in parallel above the mass 5 kg, and there is going to be a third spring which is below the mass 5 kg. So this spring both are arranged in K1, K2 are attached to the top one and K3 is attached to the ground. To solve this, what we have to do? Very simple. We have to look at what we just studied in the previous slide. We have to think about that. We have to find equivalent spring stiffness. So if I want to find equivalent spring stiffness, first let me determine it for the K1 and K2 which are in parallel. Then what is the meaning? It is simply the summation of K1 and K2. So if I put summation of K1 and K2, it is K1 is 1500 and once again K2 is 1500 Newton per meter. Summing it, it will gives you 3000 Newtons per meter. Now we have this equivalent stiffness in series with K3. We find this. What will happen? Since once again it is going to be in this way, a series manner, then what we have to do, we have to just add K1 plus K2 plus K3. Let's see that diagram clearly. It is not that since the K3 is opposing K1 and K2, it is to be considered the springs are arranged in parallel way to 5 kg. such that we are getting that K1 plus K2 plus K3 equivalent of that will give you 5000 Newton per meter. So we have the equivalent stiffness. Let me find the natural frequency omega n. The formula for finding the natural frequency is square root of K over m. That means we can substitute 5000, the equivalent stiffness here, divided by 5 kg. We have that approximately the natural frequency is equivalent to 31.62 radians per second. Finally, we find out the natural frequency in radians per second. Similarly, we can just extend this. So we can able to calculate natural frequency in hertz. Okay, the formula for that is just consider omega n divided by 2 pi. If we divided it by 2 pi, then we can able to get that 5.03 hertz. So the natural frequency of this given system is approximately 31.62 radians per second. Otherwise, it can be 5.02 in terms of hertz. So we found this by first calculating equivalent stiffness of the springs in parallel, then the total equivalent stiffness of the system, and then we are calculating the natural frequency by using this formula root of K by m. This problem demonstrates how to analyze a spring mass system with multiple springs connected in both parallel or otherwise series, but we have to understand how it has been connected and how to the formula equivalent stiffness. So in the next slide we will see the next similar kind of problem and somewhat more complex than this. The next problem is, as shown in this figure, it is a complex one which is involving combination of series of springs and series of parallel springs, and put together ultimately once again it will be connected as another series of springs. So let's have to find the natural frequency of the given system. That is our aim. So let's start with the given information. They given all the stiffness, whatever the springs. How many springs are here? 3, 4, 5, 6, 7. All the 7 springs having the same stiffness, which is equal to 2 to the power of 10 to the power of 5 Newton meter. Also, the entire stiffness of the spring is connected to a single mass, which is amounts to 20 kg. So our goal is to find natural frequency of the system as shown in this configuration. Let we see how to convert this stiffness and parallel arrangement slowly in order to get the equivalent stiffness of the entire system systematically. So if we see that, first initially I am considering only this 2. Let me see this. So these are springs are in parallel. So K plus K. Now it has been converted into 2K. Now the springs are in parallel is converted into springs in series. One spring is having 2K value, another is having K value. Now what we have to do? We have to apply the concept of springs in series. What is that? K equivalent equal to K1 into K2 divided by K1 plus K2. So if I apply this, so I can get that it is 2K by 3. Okay. So you can see that K1 by K2 is it not? It is 2K into K divided by. So we have to add it. In that case, it is 2K plus K. So 2K square divided by 3K. 1K get cancelled. So this springs on series we will get 2K by 3. Similarly, we have to go for the next one. The same system. We will go. It has been seen that now the springs are connected in parallel. Just add it. Okay. So when the springs are connected in parallel, we are just adding it. So 2K by 3 plus K, which will give you 5K by 3, so which is put up there. So 5K by 3 is now connected with, so this is equivalent to 5K by 3, and which is changed, converted into a equivalent combination of this one and connected to the series spring. If it is series, once again what we have to do, we have to use that springs in series formula, which is K1 into K2 divided by K1 plus K2. Let me see this in the next slide. We are continuing our analysis from the previous slide, that is we left over there at this juncture, that is 5K by 3 is seriously connected with K. At that case what we have to do, we have to get the equivalent stiffness by 5K by 3 into K divided by 5K by 3 plus K, which will give you 5K by 8. So now the system is rearranged to 5K by 8 spring is parallelly connected with K. So what we have to do, we have to add this. This addition will give you 13K by 8. So at last we are bringing that one step further, that is 13K by 8. This spring is connected with K. It is once again springs are in series. So if it is the springs are in series, use that formula, that is 13K by 8 into K divided by 13K by 8 plus K. This will give you 13K divided by 21. So at this final step, what we got, the entire system, see that 7 number of springs has been just we are simplified into a single spring having a equivalent stiffness of the 7 springs, such a way that we applied the concept of springs in series, springs in parallel to get this equivalent spring. Now that equivalent spring value is 13K by 21. Now we have to apply that in our natural frequency formula, that is omega n equal to root of K by m, where K is 13K by 21. We have to substitute the mass value which is given earlier in this slide. So now we substitute this, what we will get? We will get the natural frequency as 78.68 radians per second. So what we are understood from this problem is, if there is a n number of series of springs are connected in parallel, we have to convert in stage by stage to a equivalent stiffness. Then at last the single equivalent stiffness of a system will be arrived. Using that we can able to calculate natural frequency for the entire system. Let we go for some practical application in the next slide. Here we are going to tackle a problem involving torsional spring constants, specifically focusing on a propeller shaft. The goal is to determine the overall torsional spring constant for this shaft, which is crucial for understanding how it resists twisting forces. Let's take a look at this diagram. We have a propeller shaft that fixed at one end, represented by this wall. It's made up of two distinct sections. Each section is going to be represented numerically. First section represented as 1, 2, second section represented as 2, 3. Each section has its own geometry and material property which will influence its torsional stiffness. This section 1, 2 has a length of 2 meters. It has two different diameters, 0.3 meter for the first part and the inside diameter is 0.2 meter. It is a hollow shaft. Second section of the propeller shaft is 2, 3, which is having a length of 3 meters. It is also a hollow shaft. Outer diameter is 0.25 meter and inner diameter is 0.15 meter. The torque is denoted by T, which is applied at the free end of the shaft where the propeller is attached. The torsional spring constant K suffix T, the torsional spring constant is K suffix T, represents the resistance of the shaft to twisting forces. Here the KT means shaft is stiffer and requires more torque to twist it by a certain angle. To determine the overall torsional spring constant, we need to consider the individual torsional spring constants at each sections. We can calculate this using the following formulas, that is, the first section, it is going to be the torsional stiffness Kt suffix 1 2 means G into J1 of 2 divided by L2. G represents shear modulus of the material. J represents polar moment of inertia for the section. L is the length of the section 1 2. Similar way, we can also able to calculate the stiffness for the section 2 3, that is G, that is once again the shear modulus of the material into polar moment of inertia of the section 2 3 divided by the length of that particular section. We will solve it in the next slide. The torsional spring constant of the propeller shaft, we are seeing it. We are continuing the same problem from the previous slide. Now we will walk through the solution to determine the torsional spring constant. We discussed earlier, we need to calculate torsional spring constant for each section of the shaft, that is for section 1 and 2 and section 2 3, using the stiffness formula what we discussed in the previous slide. Let me calculate, that is for the section 1 2, that is G shear modulus into polar moment of inertia divided by the length. So if we substitute it, we can able to get that 80 is the value which is given, then the outer diameter, inner diameter we have to substitute, and length of the section 2, if we substitute it, for the first section the torsional stiffness is given by 25.5 into 10 to the power of 6 Newton meter per radians. In a similar fashion, we have to calculate for the section 2 3, if we are substituting the known values which is given in this figure, that is section length is 3 meter, outer diameter is 0.25 meter, inner diameter is 0.15 meter, and the shear modulus is same for both section 1 and 2. If we substitute, we will get it is 8.9012 into 10 to the power of 6 Newton meter per radians. We have calculated the individual torsional spring constants for the two sections of our propeller shaft, that is K suffix T1 of 2 and K suffix T2 of 3. Now we have to find out equivalent torsional spring constant for the entire shaft. As we discussed, these sections are connected in series. Since the sections are in series, we use the formula for combining spring constants in series. In that case, the formula simplifies to KT equivalent is section torsional stiffness 1 into section torsional stiffness 2 divided by the summation of the two section torsional stiffnesses. Let's substitute the values we calculated earlier, that is the section torsional stiffness value K T suffix 1 2 is 25.5 into 10 to the power of 6, then K suffix 2 3 is 8.9 into 10 to the power of 6. If we plug this value into the formula, we will get that the equivalent torsional stiffness of the propeller shaft, which is amounts to 6.597 10 to the power of 6 Newton per meter. Performing this calculation, we find that the equivalent torsional spring constant K suffix T equivalent is approximately 6.5997 into 10 to the power of 6 Newton meters per radian. This value, what we get is the equivalent value which is represents overall torsional stiffness of the entire propeller shafts. It is important to note that this value is lower than the previous values k suffix t of 1 and 2 or k suffix t of 2, 3, which is equal to 8.9. You see that it is first section 25.5, second section 8.9 into the power of 10 to the power 6. The equivalent value is 6.5 into 10 to the power 6 only. This is characteristic of spring series. The overall stiffness is reduced. By understanding how to combine torsional spring constant in series, we can accurately determine the overall torsional stiffness of complex shafts like the propeller shafts just we analyzed. This is crucial for predicting the shaft's behavior under torsional loads and ensuring its structural integrity. Thank you.